In this lecture, I will quickly go over the very fundamental data structures: array, vector, and list. I assume you already know the basics of C++. The first data structure is array. This line of code creates an array of size 5. The name of the array is A. Its initial value is HELLO. Such an array is created. The size of the array is fixed. Once the array is created, the size cannot grow. Elements of an array are contiguous in memory, so we can use the address of the 0th element to find the ith element. It takes constant time to access the ith element. Elements in an array can be accessed using a bracket. A bracket 1 is the first element in the array. It is assigned to the variable x. Now variable x is letter E. C++ counts from 0, so the first element in the array is E. It is actually the second element in the array, but it is accessed using A bracket 1. Elements of an array are mutable. Their values can be changed. This line of code changes the 0th element to letter B. Then the array changes from HELLO to BELLO. Previously, we created an array in this way: char A bracket n. To create an array in this way, we need to know the size of the array when writing the code. When I write the code, if I know the array will store the 5 characters HELLO, then I can fix the size to 5. However, when I write the code, the size of the array may be unknown. Consider such an application. The program needs to read a file and put the characters in an array. When I write the code, I don't know how long the file is. So when I write the code, I cannot fix the size of the array. Only after reading the file, the program knows the size of the array. This is why dynamic allocation of arrays is useful. Let's create an array using dynamic allocation. I declare pointer A. Its initial value is null. Now let's create an array and let A point to the array. Let the size of the array be n. I don't need to fix n when I write the code. N can be determined when the program is running. For example, I can use cin to read in the size. The user types a number in the command line, and n will be the typed number. When compiling the code, the program does not know n. Only when the code is executed and interacted with the user, the program knows n. This line of code asks for a memory block of size n. The address of the front of the memory block is assigned to the variable A. In this way, we get an empty array of size n. Then we can store something in the array. Here, I store the characters HELLO in the array. If the array is created using dynamic allocation, then it must be deleted when it is no longer useful. Don't forget to delete the array after using it. If the memory is not freed, there will be memory leakage. The program will occupy more and more memory and eventually break. We can use delete bracket A to free the memory allocated to A. The operating system will recycle the memory. After the delete operation, we had better assign null to the variable A. This can make debugging easier. If your code uses A again, the bug will be easily identified. Let me summarize the properties of the array data structure. First, arrays have fixed size. The size is determined either when you write the code or when the program is running. Once an array is created, you cannot append more elements to the end of the array. We are going to learn vector and list. They can grow dynamically. Second, arrays allow randomly accessing the ith element using a bracket I. The random access has only constant time complexity. Vector also allows random access, but linked lists do not. Third, removing an element in the middle has O(n) time complexity. N is the size of the array. Removing an element is slow, because the rest must be moved forward one by one. Vector has the same shortcoming. In contrast, linked list allows removing an element using constant time, which is faster. The second data structure I'm going to introduce is vector. Vector is almost the same to array. Vector is actually array with a wrap. The main difference from array is that vector's capacity can automatically grow. In contrast, the size of an array is fixed. New elements can be appended to the end using the pushback function. It takes only constant time. With the new elements appended, the size of the vector will grow. The last element can be removed using the popback function. It takes also constant time. This line of code creates a vector. Here, vector is imported from the C++ standard template library. V is a vector created by the line of code. It is essentially an array. Similar to array, vector uses contiguous memory. So as well as array, vector supports random access. The major difference from array is that the size of vector can automatically grow. Elements in a vector can be accessed using brackets, just like array. V bracket 1 is the first element in the array. C++ always counts from 0. In this example, the first element is the character E. Values can be assigned to elements of a vector using brackets. This line of code changes the zeroth element from H to B. The size of a vector can grow automatically. The function pushback can append new elements to the end of the vector. This line of code adds a character S to the end. Now the size of the vector grows. The function popback deletes the element in the end. After running the popback function, the back pointer moves leftward. The erase function can remove any element in the middle. I use v.erase parentheses v.begin plus 1 for removing the first element, that is, character E. After the element got deleted, there will be a hole in the middle. The rest elements will move leftward to fill the hole. While vector allows the deletion of elements in the middle, frequently running the erase function is a bad idea. On average, the time complexity of the erase operation is O(n). It's much slower than the operations such as random access and pushback. Vector capacity can dynamically grow. Here's an example. I create a vector v with capacity 100. The parentheses after v specify the initial capacity and size. Now vector v has 100 elements. All the elements are zeros. v.size returns the size of v. Now it is 100. It means that v has 100 elements. v.capacity returns the capacity of v. It's also 100. Capacity is different from size. I will elaborate on this point in the next slide. Pushback x means appending the character x to the end of the vector. Now the size becomes 101 because there is one more element. But the capacity becomes 200. Now I explain the difference between capacity and size. There is an array wrapped inside the vector object. The size of the array is the capacity, that is 200. Now there are 101 elements in the array, so the size is 101. Size cannot exceed the capacity. Previously, the capacity and size are both 100. After the pushback operation, the size tends to exceed the capacity. What happened when the size is going to exceed capacity? A new array of capacity 200 is created. All the 100 elements in the old array are copied to the new array. Put the new element in the 101st position. Finally, free the old array from memory. This process is slow, so the library tries to avoid this process. The library uses the strategy of allocating more space than the current size. While it doesn't need 200 spaces for the 101 elements, the vector reserves more vacancy in case of future needs. The third data structure is list. The list data structure in C++ STL is actually the doubly linked list. This is a node of the doubly linked list. The node can store some data. It has two pointers. One points to the previous node, and the other points to the next node. This line of C++ code creates a doubly linked list. The variable name is L. The 5 characters HELLO are stored in the list. This is what a doubly linked list looks like. Each node stores a character. Each node is connected with 2 nodes. Each node has 2 pointers, the previous pointer and the next pointer. The previous pointer of the first node is now. The next pointer of the last node is also now. The size of a linked list can dynamically increase or decrease. It is easy to insert or delete a node. The nodes are not contiguous in memory. The nodes can be dispersed everywhere in memory. So we don't know the address of the ith node. Random access is not feasible. To access the ith node, we have to start from the front and move I steps. We have learned array and vector. They both allow random access to elements. Differently, list does not allow random access. Here are 2 examples. I want to access the second element, so I want to use L_2. But it doesn't work. The compiler will raise an error. I want to assign the character A to the 0th element, so I try to use L_0. It doesn't work either. An error is raised by the compiler. Lists can only be visited sequentially. That is, we have to start from the front and move 1 step each time. To read or write the ith element, we have to move I steps. This can be slow. If frequent random access is required, then array and vector are better options than list. The linked list has 2 pointers. One points to the front and the other points to the end. Getting the front and the end elements is fast. Only constant time is needed. L.front returns the data in the front node, that is, the character H. L.back returns the data in the back node, that is, the character O. In contrast, accessing elements in the middle can be slow. we have to use an iterator that moves from the front or back towards the middle. To traverse a linked list, we need to use iterator. This line of code creates an iterator that points to the front of the list. Its type is list char iterator. I use iter as the name of the iterator. *iter is the data stored in the node. When I print *iter, the program shows the character h. This line of code is iter++. It means moving the iterator one step rightward, so the iterator will point to the next node. Now I print *iter again. This time, the program will show the character e. We can modify the data in the node using iter. This line of code assigns character a to *iter. It changes the data in the node from character e to a. Elements can be inserted into the list. The pushback function appends a new element to the end. This line of code means appending the character s to the end. This line of code creates a new node. Its data is the character s. The new node is linked to the previous node. The back pointer of the linked list now points at the new node. The pushback function has only constant time complexity. It's very fast. The pushFront function means to insert a new element to the front. It works in the same way as pushback. A new node is created, and it is linked to the old front. The pushFront function has only constant time complexity. It is one of the advantages of the linked list. You can insert new elements into the front of a vector, but it is slow. All the existing elements need to be moved one step backward, so it costs O(n) time. The nodes of the list can be deleted. The popback function deletes the last node in the list. It works in this way. Delete the last node. Let the back pointer point to the previous node. Set the next pointer of this node to now. The popback function has constant time complexity. It's also fast. The popFront function deletes the first node of the list. It first removes the front node. Then, let the front pointer point to the next node. Set the previous pointer of this node to now. The time complexity is also constant. Besides, nodes in the middle can be deleted. Nodes can also be inserted into the middle. If we know the address of a node, we can perform the insertion and deletion operations in constant time. Recall that vector also allows the insertion and deletion operations in the middle. But such operations are slow. They have O(n) time complexity. In contrast, lists can very efficiently insert and delete nodes. Let me summarize this lecture. We have learned three kinds of data structures: array, vector, and list. Here, I compare the three data structures. Array has a fixed size. We can either specify the size when writing the code, or dynamically allocate memory when the program is running. In either way, once the memory is allocated, the size of the array cannot be changed. We cannot append new elements to the end of the array. The size of vector and list can grow dynamically. New elements can be appended, and the size of vector and list can grow. This is a comparison of the memory management. Array and vector use contiguous memory. That is, If two elements are neighbors, then they are next to each other in the memory. If we know the address of the 0th element, then we know the address of all the elements. We can thereby access the ith element using only constant time. This is known as random access. Linked list does not support random access. Elements are stored in the nodes. The nodes are not neighboring in the memory. Because list does not use contiguous memory, random access is infeasible. To access the ith element, we have to start from the beginning and move I steps rightward. Here is a comparison of some frequently used operations. Array and vector allow random access, so the time complexity is constant. List does not support random access. Pushback means appending a new element to the end. Array has a fixed size, so it does not support pushback. The size of vector and list can grow dynamically, so they allow pushback. On average, vector performs pushback in constant time. Occasionally, pushback is slow. It is because when the size reaches the capacity, a new array is created, and the content in the old array is copied to the new array. Pushback of list is always fast. The time complexity is always constant. Popback means removing the element at the end. For both vector and list, popback is always efficient, only constant time complexity. Insert means adding a new element to an arbitrary position. The size of the array is fixed, so insertion is not supported. Vector allows insertion, but it can be slow. Elements to the right of the position must be moved one step rightward to make room, so that the new element can be inserted. On average, the time complexity is O(n). List can perform insertion very efficiently, only constant time complexity. Erase means deleting an element in an arbitrary position. Vector supports the erase operation, but it is slow for the same reason as the insertion operation. List can perform erase very efficiently, only constant time complexity. We have learned 3 data structures. Which one shall we use? If you need a fixed size memory throughout, then array is the best option. If the size is varying, for example, you need to insert new elements or delete existing elements, then you will need vector or list. If frequent random access is required, then vector is recommended. The downside of vector is that insertion and deletion in the middle are slow. The advantage of list is the fast insertion and deletion at any position. The downside is that list does not allow random access. To visit the ith element, you have to start from the front and move I steps. This is much slower than random access. Okay, this is the end of the lecture. Thank you for viewing. The link to my slides can be found in below.